Thank you for the opportunity to present. My name is Michael Boyd, and I live in California in Santa Cruz County. First, I introduce, back in August of last year, I published a paper in the IEEE Sensors Journal titled Resolving the Extra Dimensions for Gravity. It presents experimental evidence for magnified gravitational and anti-gravitational forces at nanoscale distances using nanobumps and nanopits on a spinning hard disk platen. The study employs a GMR sensor positioned 100 nanometers above the disk surface and piezoelectric transducers to measure forces. This article uses the measured forces for a bump, gravity force produced by a bump, and by a pit that were measured in nanonewtons force. This is from table 2 of the Resolving the Extra Dimension for Gravity paper, and expresses the Casimir force in nanonewtons too. The input data is shown for my analysis is shown in table 1 of the paper, which I'll show here too. The results are presented in tables 2, 3, and 4. 3 variable length nanopits show non-renormalization of spacetime. Okay, what's inside a hard disk drive? On the left here, you can see the hard drive. There's a disk platen, and then there's a what's called an actuator, and an actuator arm, and then sitting on the end of the arm is this little device that's shown on the left top here, and they call it a slider because it kind of looks like a sled. And so basically what happens is there's on the underneath the thing where the closest distance between the surface of the rotating disk and the slider, they locate a read write head, it's called, and on the lower left you can see that. And there's like a little microscopic coil that they use to write the magnetic data on the disk, and then there's a device called a MR or GMR resistor, which stands for giant magnetoresistor. That's the read sensor. And you can see on this image there's magnetic bits written below it, where basically the data has one bit going north and the other going south. And that's what's on your hard disk inside. Now that GMR sensor is kind of the key to the measurements that are going to follow. Now the disk, what I did is I fabricated on the surface of the disk little nanobumps and nanopits along a radius, and the dimensions are there on the left. Essentially, I did that with a thing called a focused ion beam, which is a kind of like an electron microscope, but it shoots ions. And the bumps were made with tungsten metal, and the pits were etched with beryllium. Now, what I discovered in my prior paper is that this other physicist named Harold Hal Puthoff, he wrote this paper back in 2010 called Advanced Space Propulsion Based on Vacuum Space-Time Metric Engineering. And essentially what he proposes is that when you get closer to a mass, like a star, the clocks run slower. And things slow down, and objects get shorter. Okay, and now the opposite occurs as you go into, and I forgot to mention, when you're closer to the stellar mass, space-time is denser. Now the opposite is true is when you go away from the mass, like to outer space, there space-time is different. It's expanded, and clocks run faster. but rulers get longer. So these are basically related to general relativity. They also have to do with how fast things are moving. So that's basically his theory. And then what I did is I tried to test that theory. And the context here is my nanopits are creating expanded space-time below the sensor, and the denser, the nanobumps are creating denser space-time. Now, what I have here is a GMR readback signal from a 10 micrometer by 10 micrometer square bump spinning at a constant linear velocity of 12.7 meters per second. And now the disk is spinning counterclockwise, and you can see the first electromagnetic pulse there on the left. And then that's followed by a gravitational induction signal from the mass. And then after that, there's another electromagnetic induction signal produced. And the reason I know that's electromagnetic is because it's caused by the square shape of the edge of that nanobump. It's a sharp turn, so that makes the magnetic field direction change. Now, what I have here is a cross-sectional view of this slider, and on you see it's pointing to where the GMR sensor is on the lower right, and then on the lower left, it's pointing to a green box, which that represents what's called a piezoelectric transducer. It's a crystal that if you tap it, it produces a voltage. And so what I'm doing there is I'm showing that the presence of matter moving under the sensor produces a pull force and a negative polarity gravitomagnetism. Now, when I did this opposite with the nanopit, it produces a push force and a positive polarity gravitomagnetism. Now, I did these measurements, and this is table 1. This is table 2 from that previous paper. And the important thing is this calculated G-force factor here on the far right. Pay attention to that, because I'm going to show you that is important for when we're figuring out effective mass, because the mass, the calculated mass, I can get from the geometry of these bumps, for example, and then I can figure out how much it should have weighed and how much force that would produce. Well, what I measured was a lot greater, and this area on the left here, that shows what the magnification factor is. Now here's some of the constants that I'm using, like pi and gravitational constant, the density of tungsten, because the bumps are made of tungsten, and chromium because the disk is made of chromium, and that's relevant to the nanopits. Now here I have a picture of a 40 micron by 40 micron square bump, and it shows, you can see here that it measured the frame dragging. The gravitational frame dragging was 3.23 microseconds. The other thing you see is that the voltage is 2.016 volts. Well, 1 volt is equivalent to 1 nanonewton of force. So this is a 2 nanonewton force, negative 2 nanonewton pull force that I measured. Now, to calculate the mass and the speed of gravity of the tungsten nanobump, I take the volume, which I showed here was like 54 cubic micrometers. I have the density of tungsten here, and then I configure the mass is the density of tungsten times the volume, which works out to about 1.04 nanogram. The measured frame dragging is 3.2 microseconds, which I showed you there. That's over the distance between the nanobump and the sensor, which is 67.7 nanometers. Now, from that, I can figure out what the speed of gravity was. And in this case, it was 2.09 times 10 to the minus 2 meters per second. Pretty slow, a lot slower than the speed of light. So next, from that, and then I can calculate the linear and angular momentums. And the linear momentum is just the mass times the velocity. And the velocity is a fixed number, 12.7 meters per second. From that, I get for this 40 by 40 nanobump, I get a linear momentum of 13.2 nanogram meters per second. And now for angular momentum, you just multiply it by the radius, and the radius is 1.75 inches. So I get 0.587 nanograms per meter squared per second for that. And then now I'm going to apply the Puthoff model. I mentioned this before. We're figuring out the effective mass. So we take the effective mass is that gain factor. In this case, it was 195.6. We take that and we multiply that times the measured mass, or the calculated mass, pardon me, the 1.04 nanograms, and we get 203 nanograms. Now we redo the linear momentum and angular momentum with the effective mass, and we get the linear momentum is 2,584 nanogram meters per second. The adjusted angular momentum is 11.5 nanogram meters per second. Now comes the fun stuff. We're going to talk a little bit. We're going to apply this to Einstein's field equations, where G mu v mu nu, excuse me, is the Einstein tensor, and T mu nu is the stress energy tensor. G is the gravitational constant, and C is the speed of light. For a point mass, the stress energy tensor approximating the nanobump, the stress energy tensor is dominated by the mass energy component, which is the density times the speed of light squared, where the effective mass is 203 nanograms, and the Dirac delta function, there's a delta cubed R. It represents the point mass of the nanobump's position. Now we plug into that Einstein's field equation. We plug in, get rid of the c, the speed of light c, and we substitute the speed of gravity that we measured, and then we get another value for a different value for that. And then there's what's called the metric perturbance due to the frame dragging, or a lead throwing effect, which is approximately this Einstein's tensor. And so from that, what we got was this about 5.562 times 10 to the minus 13. It's in the second squared per cubic meter. This describes the curvature of spacetime due to the nanobump's effective mass increase, adjusted for the frame dragging effect and the modified speed of gravity. Then we look at the impact of the frame dragging and general relativity effects. The frame dragging, remember, we measured was 3.23 microseconds. Then we can get what's called the lens Thirring precession, where the lens thirring precession is approximately equal to the gravitational the gravitational constant times the moment of inertia times omega divided by the speed of light squared over the r cubed. that's a lot to follow, but if you look, you see here, I do the calculation, and it's in this case 4.815 times 10 to the minus 17th rads per second. Table 2 shows the results of this analysis for all 7 nanobumps. And here we see table 2. And we can see all these. Nanobump 1 we talked about. And you can see there's, this is, that I basically did it for all 7 of the nanobumps. Now there's this other thing. It's called the Casimir force, and it arises from quantum vacuum fluctuations, where the 0-point energy of the electromagnetic field between 2 uncharged parallel plates leads to an attractive force due to the restricted virtual photon modes. The force is calculated using the ideal parallel plate, where the Casimir force is equal to pi squared times the reduced Planck constants times the speed of light over the area of the plate divided by 240 times the distance to the 4th power. So now I plug in my values for our 40 by 40 micron square nanobump, and then I plug in the value for the distance, which is 67.7 nanometers. And I come up with, going through all the math, I come up with 1,035 nanometers, which is like a lot more than I measured. The results for each nanobump for the measurement distance, the Casimir force, and the lens thirring effect are shown in table 4. Okay, now let's talk about a nanopit. We have here the GMR signal from a 40 by 40 micrometers square nanopit. The figure shows that the nanopit had a measured gravitomagnetic force signal of 378 millivolts, or 378 or 0.378 nanonewtons of force. Now let's do this same calculation again with the we go through the same calculation with the nanopit, and we get that the missing mass is 0.55 nanograms, that the linear and angular momentum are -7 nanograms per meter second squared, and minus 2.5 times 10 to the 4th nanograms per meter squared for the angular momentum. We calculate the missing mass by using the volume times the density of chromium, 7,190 kilograms per meter cubed. We calculate I already did that. Sorry. Calculate the speed of gravity in Einstein's field equations. Here we measured a 3.3 microsecond frame dragging. Our distance is the distance to the bottom of the pit to the sensor, which in this case is 143.2 nanometers. We calculate the speed of gravity as 4.34 times 10 to the minus 2 meters per second. And we do the Einstein's field equation, and we come up with a negative 8.24 times 10 to the minus 13 seconds squared per cubic meter. The results for all 7 nanopits are shown in table 3. And here's table 3. And then I look at the Casimir force, and we came up with minus 11 nanonewtons of Casimir force, which is a lot more than we measured again. And then the other thing is we calculated the tunneling barrier, which is there's a 1 over r cubed force dependence for the nanopits with imaginary roots that suggesting a potential barrier, e.g. in this case that we're looking at, 0.378 nanonewtons for nanopit 1 to tunnel through it. So to calculate the barrier, we take the barrier width, 143.2 nanometers, and multiply that by the 0.378 nanonewtons, and we come up with 5.4 times 10 to the minus 17 joules. That's the potential barrier. The results for each of the nanobumps and nanopits for measurement distance, Casimir force, lens throwing effect are shown in table 4. The table also includes the tunneling barrier in joules for the nanopits. And here is table 4. And the Puthoff model predicts that in expanded space-time, nanopits, clocks run faster, causing an anti-gravity pre-signal. Here we see this 10 micron squared nanopit had a 20 nanosecond pre-signal. Now let's figure out from that the anti-gravity pre-signal in comparison to the speed of light. So we take the time for the light to travel the distance, which is that 151 nanometers over the speed of light, and then we know that time, and we compare that to the 20 nanoseconds. 20 nanoseconds is huge, so it's basically negligible. Then from that we can get that by measuring the speed of light, take the speed of light and divide it by the 20 nanoseconds, we come up with that the pre-signal is 3.9 or 39 million times faster than the speed of light. To a non-expanded space-time observer, consistent with Puthoff's model, prediction of faster clocks in expanded spacetime. The Puthoff model also predicts that in denser spacetime, clocks run slower, causing a gravity post-signal. We measured that to be 20 nanoseconds in this example of the 10 by 10 micron squared nano. And we go through the same calculations again, and we determine that the nanobump, the gravitational signal was 8.8 or 88 million times slower than the speed of light, consistent with Puthoff's model predicting slower clocks in denser spacetime. Now, the other thing is, I found that with the variable length nanopits show that we have non-renormalization of spacetime. The pre-signal factor, 23,610,000 times for all 3 nanopits, indicates a consistent faster than light effect. In standard quantum field theory, such effects would lead to divergences, e.g. the causality violation amplitudes. But the stability of this factor across different nanopits suggests a non-renormalized quantity, potentially protected by the extra-dimensional space-time structure or symmetry in the Puthoff model. Am I out of time?
It's okay, Professor.
Keep going? Okay. Now, there was quite a bit of criticism of this Puthoff model, and I'm just going to read some of the criticisms. Lacks empirical grounding, violates energy conservation. Manipulating quantum vacuum for propulsion requires infeasible energy inputs. Extra-dimensional models, e.g. Toulouse-Klein, speculative, lack direct evidence. Vacuumetric engineering, theoretically adventurous. Speculative quantum field theory interpretations. Casimir effects doesn't scale to macroscopic gravitational manipulation. Casimir force is well documented in the nanoscale, but challenging to extrapolate to macroscopic scales. Holographic perspectives suggest vacuum energy interpretations need careful quantum gravity considerations. Metric engineering faces general relativity energy condition challenges, causality/energy issues, and faster than light travel. And my conclusions are, Einstein's tensor values were confirmed the methodology accuracy. Anti-gravity pre-signal and gravity post-signals validate Puthoff's model. Tunneling barriers 8 times 10 to the 18th joules to 5 times 10 to the 17th joules support quantum tunneling. Larger nanopits, e.g. the nanopit 1, 77 micrometers cubed, show higher barriers. Casimir force, e.g. 1035 nanonewton nanobump 1 exceeds measured forces, suggesting distinct mechanism. Glass nanobumps isolate the gravitomagnetic effects. Semiconductor model explains diode-like behavior. Carrier lifetimes of a microsecond align with frame dragging delays influenced by bump or pit geometry. Boyd's data validates Puthoff's model, counters criticism, and supports extra-dimensional effects, 1 over r to the 4th power, and general relativity frame dragging. Advanced unification of classical and quantum gravity, providing experimental foundation for metrics engineering. The results and figures collectively suggest that the gravitational and anti-gravitational interactions at the nanoscale distances are stable and finite, supporting the idea of non-renormalization in this experimental context. And that's it.